I'd like to introduce our next speakers, so Sebastian and Taliesin. I'm sure many of you know them already, but for those of you who don't, they both started as students at the University of Cape Town, where they met. Sebastian finishing his PhD in theoretical physics, and Taliesin his honors in pure maths. They both began their successful careers at Wolfram Research, where they designed and developed various deep learning functionality for Mathematica, and they're currently on sabbatical, so I'm sure everyone's excited to see what they're going to do next. They're active members of the Indaba community, so give an extra warm welcome to our Wolfram Dynamic duo.
Cool, hi. So today's talk is going to be about discussing what we can learn and what we have learned from basically the only general intelligence system that we know of, which is the human brain. So we're going to start out with a quote that will sort of guide the rest of the talk. So this is from Demis Hassabis, who is the founder of DeepMind. In 2017, they wrote a nice review paper about this sort of thing. And he said, the benefits of developing AI of closely examining biological intelligence are twofold. So first, neuroscience provides a rich source of inspiration for new types of algorithms and architectures, independent of and complementary to the mathematical and logic-based methods and ideas that have largely dominated traditional approaches to AI. And the second thing is that neuroscience can provide validation of AI techniques that already exist. So if a known algorithm is subsequently found to be implemented in the brain, then that is a strong support for its plausibility as an integral component of an overall general intelligence system. Okay, so that's what the inspiration is going to be for this talk. And the sort of roadmap, just so you know where we're going, there's going to be 3 parts. So the first part is we're going to look at some existing historical inspirations that neuroscience had for machine learning methods. The second thing is that we're going to see how Tali is going to present about how neuroscience can validate machine learning. So we're going to look at, in this case, dopamine as a reinforcement learning reward prediction error. And the final thing is, why should we even care at the moment? So there's some schools of thought, I'm not going to accuse anyone here particularly of that, but isn't deep learning already superhuman? So on things like ImageNet and Go, it can do as well as humans or better. So I'm going to hopefully motivate that we're not at all there yet. Like humans are still vastly superior in many areas, and I'm hopefully going to convince you of that in section 3. Okay, so to start out this tour of sort of inspirations, there's going to be a whole list of things that sort of came from neuroscience. I'm not going to go through all of these things now, but basically this is just to show you that there's a whole bunch of things. And there's a nice article at the bottom that you can read for more information about some of these. Okay, so the founding inspiration is the artificial neural net. So this is an actual neuron. At the bottom are dendrites, and the dendrites collect the information, and they lead the information upwards to the axons, which then connect to other dendrites. And the middle part there is the nucleus of the body of the neuron. So this is really the sort of one of the first machine learning methods that came out, was people looking at these neurons in the brain and saying, how can we make a very simplified mathematical model of them? So the sort of original people that did this were McCulloch and Pitts, I'm not sure how exactly you pronounce that, 1943. And this is still sort of in use today. So just multi-layer perceptrons are just many of these kinds of neurons sort of stacked on top of each other. Okay, so one very simple question that I think everyone in machine learning should sort of understand is how many neurons really are in the brain? Like how the neural networks that we've got currently, how do they compare to neural networks in the brain? So, the number of neurons in the brain is about 10 to the 11. The number of synapses, which is the number of connections, is in, let's say, a ResNet. This has 10 to the 7 parameters. Whilst in the brain, it's about 10 to the 14. So what's crazy about that is that if you took every parameter in ResNet and replaced each of those parameters with another ResNet, that's when you get something similar to what the brain has. But even then, you're not done. Okay, actually, one more thing. Yeah, so the brain also doesn't use much power. It uses about 25 watts, which is about a fourth of an incandescent light bulb. But it gets worse. So the brain, even the synapses in the brain, for an artificial network, we represent those as real numbers. But in the brain, they are actually vastly more complicated. So this is from Ganguly from Stanford, who writes, in artificial networks, synapses are modeled by a single scalar value. In contrast, every biological synapse has hiding within it immensely complicated molecular signaling pathways, hundreds of different types of molecules capable of implementing an entire dynamical system with sophisticated temporal processing capabilities. Oops, why is it backwards? And the whole book's about dendrites that are computing and the computations that they can do. So these are, even if you have, if you replace every parameter in a ResNet with another ResNet, you're still not done. Each of those parameters is still a dynamical system that can do all kinds of computations. So I just want to give you some idea of the scope of just how complicated the brain is and how far away sort of artificial networks are of even coming close to the complexity that the brain has. Okay, just a few things that are also useful to know about. Like the brain has many different kinds of neurons. So in this case, it has, well, there's a whole collection, and they're all different kinds of things. And this is also interesting for us, for machine learning. Like, why did evolution decide to create all these things? Also, the thing that's very important is that it doesn't use continuous signals. It uses spikes. So neurons emit either a spike or no spike. And these are sort of spike trains of measurements of these neurons emitting things. And this has directly inspired things like neuromorphic processors. You probably haven't heard much of these yet, but companies like Intel, IBM, they're all sort of racing towards building chips that can do spiking neural network implementations at a hardware level. For efficiency, basically, that use very, very low amounts of power and that can do very, complicated things. And then, okay, so this is some very direct inspirations that we've had. So we're going to go through a few more things, and Talie's going to do that now as well. But before that, there's one very simple thing that I'll end with, which is attention. So this was directly inspired by thinking about how humans sort of look at things, that they pick out, relevant information and images. They don't look at everything equally. And this has sort of been key to improving all kinds of models, from machine translation to image processing models. So here's one example where the model returns what is in the image. And you can see exactly in this image what the model is actually looking at with the white. Okay, so Talie.
Thanks. And something I want to mention quickly about attention is you can see how powerful it is to have introspective access into your model to see what it is attending to. So that's especially important if you want to know why it made a mistake and what you might need to change about your model, or to explain why performance is good in some cases. So the other example of a sort of classic example of where deep nets have been inspired by neuroscience is in vision. And the history of this goes back quite far. So first I should mention that one of the key components of all today's modern convnets that we use are these three kinds of layers: convolution layers, pooling layers, and batch normalization layers. So here we're seeing a little diagram of inception, and the colors represent those three types of layer. So you can see that they sort of all playing a role here. And all of these were had their origins in models from neuroscience that were originally designed to better understand what's going on in the brain, and sort of gave rise to this inspiration that we used in deep neural networks. So I'm going to focus on one of those, which is specifically convolution. So convolutions actually began in this model called the neocognitron. So this is from the 1980s. This is a researcher called Fukushima. And if you look at that picture on the bottom left, you'll even recognize some of the diagrams that you see today to illustrate how convolution works. So to explain one of the motivations for how we got to convolution, I'll just recap a little bit of how the brain sort of processes visual input, not in any real depth, but just enough to give you a flavor of what's going on. So the concept I want to get to is called retinotopy. And that's the idea that different parts of the brain in the visual cortex process parts of the image that come from a small patch of the image. So if we look at a particular patch of neurons in the visual cortex, we can see that it's only involved in processing a small part of the visual scene. So here are some experiments that were done with MRI. So what these demonstrate is these are animations that are shown to people. People fixate on the little cross in the middle of the image, and these animations, the one on the left will expand outwards, the one on the right will kind of spin in a little circle, and as they expand, you see a kind of wave of activity happen in the brain. So in the visual cortex, the neurons that are kind of further towards the back are involved with parts of the scene that are closer to the center, closer to where you're looking, and as it expands outwards, you see this activity sweep across. So that's kind of like getting at this idea of retinotopy, which is that parts of the, individual parts of the brain don't see everything in your visual scene at once. They're not affected by everything at once. So let's see how we can put that in a computational model. So if we treat images as just kind of dense sets of values, of pixel values, and we sort of process them with traditional fully connected dense layers that you might use in a sort of deep learning framework, then you'll notice that each unit in the output is connected to every single pixel in the input. But if we use this kind of inspiration of retinotopy, we can limit that a little bit, and we can say that each unit in the output is only affected by a small patch of pixels in the input. So what advantages do we get from this? So one is that we use drastically fewer parameters to kind of transform the input image into an intermediate representation. So if the image is of size n, then we go from n to the power of 4, because it's n by n pixels that have to connect to n by n pixels in the next layer. We go from that to n squared by k squared. K is the size of that receptive field that you saw there. It's the size of this little box. That's 3 in that little diagram. But if we introduce weight sharing, in other words, the form of transformation between each little patch in the input to the output is the same for every single pixel in the output, then we can bring that down even more, so we can bring it down to just k squared. And to give kind of actual concrete numbers for like a real problem, if you have an image that's of 256 by 256 and kernels of size 4, then the savings you get in the number of parameters is roughly 1 billion. So that's an amazing kind of compression of the number of weights you need to represent this transformation. And perhaps a more important point is that it encodes something that a prior that we have about image processing and specifically object recognition, which is that it doesn't matter where an object is in an image to its identity. So a cat on the top left of an image is also a cat if you move it to the bottom right of the image. Now, that's not exactly how the brain works. There's no notion of weight sharing in the brain. But if you think about it, it's how the combination of your brain and your eye in a kind of feedback loop works. And that's because your eye jumps around. So you have a part of your retina, which is right at the center, it's the fovea, that has very sort of detailed kind of high definition. And then you've got very kind of low definition around that. So your peripheral vision is not very acute. And that means that as you kind of gaze at different parts of the scene, you're really applying the same weights, the weights that are associated with the kind of patch of transformations in the center of your vision. You're applying them again and again and again. So that's similar to how a convolutional layer works. It's applying the same kind of rough processing to every single point in the input image. So that's vision, and that's a kind of a little, very kind of sketched out history of how neuroscience was used to sort of drive some of the breakthroughs that we had in deep learning in the last 10, 15 years. But let's look at the other direction. So let's look at validation. So what I mean by that is, if we look at some of the ideas that we've sort of invented independently in machine learning, do we find analogs for them in the brain? And the example I'm going to look at is something called TD learning. So that stands for temporal difference learning. And you can wait for Jonathan's talk tomorrow, where he'll go into more detail about reinforcement learning. So I'm not going to give much more than just a sketch of what that looks like. TD learning is just a simple technique for training a model-free reinforcement learning algorithm. It uses something called a value function. And a value function is an estimate that an agent has for how good it is to be in a given state. Once you have an accurate value function, you can choose actions easily. So you can just say, which action will yield the most valuable state? And I'll take that action. So let's work through a little example. So let's say I'm sleeping in my bed, my alarm goes off, and I want to decide between two actions. One is to hit the snooze button and keep sleeping. The other is to get up and go about my business. So let's say the way I think now, it's much more pleasant to be sleeping than it is to be getting up and confronting the cold, bleak reality of my winter morning that I'm in. So I'm going to choose to hit the snooze button. But there are consequences to that. So I may be happy now, but an inevitable consequence of that is that I'll be late for my job at Metacortex Corporation, my boss will chew me out, and then I'll lose my job. And that's bad, right? So if this is the predictable consequences of my action, TD learning can help me update my beliefs about the values of being in each of those states to be more accurate. So this sort of delta here is the sort of difference from time step to time step of my estimate of the value of that situation. And if I propagate those errors backwards and kind of update my beliefs, the next time I have a job and I'm confronted with the same problem, I will realize that hitting snooze is really bad. It's a bad state to be in. And instead I should take the less bad option. Not great, but it's not as bad as Agent Smith coming for me. So I'm going to pick that, and I'm going to go with that in future. Now, obviously, this is not how real people learn not to be late for work. So that's why it's a sketch. And you can also see why it's model-free. The way we would kind of deal with this is to plan ahead and realize the consequences of our actions in advance. And that would be a model-based reinforcement learning algorithm. But it is a good model for how some animals deal with certain tasks where they're given rewards for making certain choices. So let's look at one of these experiments. First, a little bit of background about dopamine. I'm sure everyone's heard about dopamine. I won't go into very much detail. I mean, we know that it's associated with pleasure, with reward, compulsive behavior, addiction, all kinds of things. We still don't know exactly what it does and what it's good for. So let's look at some experiments that were done. So this is a volunteer for the experiment who's enjoying some nice fruit juice that he can sip from this strange-looking apparatus. He gets that when he successfully completes some task. And let's look at an array of electrodes that's going to be embedded into the monkey brain. And they will be recording the activity of what are called dopaminergic neurons. So those are neurons that produce releases of dopamine in the brain of the monkey. So what you should read this graph as is going from left to right. So time progresses from left to right. And you're seeing the individual spikes of individual neurons that are being recorded from this electrode array. And if you sum the number of spikes, then you can get a sort of summary of how active all of these neurons are in concert, and that's the sort of bar graph on top. Now you'll see that there's this banana event that happened. That's when it got a little reward of sippy of fruit juice, but it wasn't expecting that reward at all. So it had no reason to believe a reward would come. It just suddenly came. And you'll notice, first of all, before I introduce the stimulus, you'll notice that those things spike. So they have this background rate, and then there's a sudden kind of spike of activity that's a sort of concentration of activity that's associated with that reward just after the reward actually happened. Then we introduce a stimulus, and at first nothing changes. But as the animal learns to associate that stimulus with that reward, a strange thing happens, which is that dopamine activity gets shifted back towards that stimulus, and it stops happening for the reward. So now that it expects a reward after it's heard the bell, it has no reason to produce more dopamine. And if you think dopamine represents just pleasure, this is completely surprising. Why wouldn't it get pleasure from getting the juice? Something else interesting happens. If it doesn't get that reward, then there's an actual depression in the amount of dopaminergic activity. So what explains this? Well, there's a simple interpretation, which is that dopamine represents the error in the prediction of reward, of future reward. So if an animal's job is, among other things, to predict the value of its current state, part of that involves its expectations about future rewards it'll get. If it knows it'll get them, then the value of being in the current state is still high. Changes in its dopamine can then correspond to an error in this prediction that can help it to learn a Q function. So I don't have too much time to go into that, but I'll get to that later. So if you have, we're running a little bit low on time, so maybe I should try to accelerate this a little bit and pass this back to Sebastian. So a quick summary is that in the sort of canonical example of a surprising thing, if you think dopamine just represents hedonic value, right? If it represents just pleasure, if you import concepts from reinforcement learning, you can better understand what might be going on in these animal experiments. And that's considered one of these sort of like really satisfying results of where reinforcement learning can tell us something about neuroscience, and where it can provide validation that the ideas we're generating in the domain of reinforcement learning are somewhat on the right track, like they related to something that actual animal brains are doing. So that's just what I said there. There are other examples of this in vision, but I don't have really time to go into that. There's a fantastic blog post by Grace Lindsay that I will shout out as if you want to learn more about the connection between computer vision models and deep visual cortex.
Cool, thanks. So, this is the most polemical part of this talk, I think. So, the first thing is, neural networks have been quite successful. I won't deny. So, I'm just going to go through some very quick examples of just how successful it's been. So, things like Google Translate, they moved to using neural networks in 2016. As dawn broke over Tokyo, Google Translate was the #1 trend on Japanese Twitter, just above some cult anime series and the long-awaited new single from the girl idol supergroup. Everyone wondered, how had Google Translate become so uncannily artful? And the reason was that they'd switched to neural networks. To things like object detection, or giving masks around all the different objects in the image. To things like this, like generating faces with generative adversarial networks. Very, very impressive. To earlier this year, playing StarCraft and actually beating a human professional, although there might be some dodginess there with too good micro abilities. Then also just, a few days ago, there was Dota. So I don't really understand Dota. That looks very strange to me. So this was on Saturday night. I think there was a big tournament against the world champions, and OpenAI won. Okay. So, and vast numbers of other applications, from things like protein folding at DeepMind. This is currently the state-of-the-art method for figuring out how a protein will actually look like once you just give it the sequence of peptides. To things like SETI searches, like finding extraterrestrial life. Like these are very common. Like neural networks are integral components for those. So the applications are very impressive. However, is it just how good is AI currently? So, what do you think will happen here? So, robot soccer is a good example of, just to show how bad AI currently is. When it has to do all kinds of things simultaneously, so vision is important here, controlling control systems. Okay, it's rather embarrassing. It does eventually kick. There we go. So sad. So this is an example of just how, as an integrated intelligence, like humans are vastly superior to machines currently. And here's a few things that sort of humans can do that machines are struggling with a lot. So one is playing games. So humans can learn to play games very, very fast. So this is Atari Frostbite. And this graph shows just how long it takes for different things to learn. So these are some DQN networks. And even after 900 hours of playing, they're still not quite as good as humans. There are better algorithms now that are much faster, but still, humans learn less than 2 hours. So it only takes about 2 hours for a human to get very, very good at this game. And the very simple reason for that is that humans can transfer their knowledge from one domain to another. So Hassabis again, I think the transfer learning is the key to actual general intelligence, and that's the thing we as humans do amazingly well, and currently machines cannot do that. So I think it's actually one of the big challenges to be tackled towards general AI. And other things as well. So for example, if you have a new environment, so if you train neural networks on some sort of environment like this, breakout, and you just change the game just slightly, so like you just raise the paddle a bit, or you have a center wall where the ball can't hit the things behind, DQ and trained networks, they completely fail. They just don't work. Whilst humans, they can reason and say, oh, this is just one small extra change, we can quickly adapt to this new problem without having to be retrained for 900 hours. Other things, I mean, this is like, if humans have no difficulties with this sort of thing, this is just
our software.
This is our software in Mathematica. So ImageNet models, they haven't seen a lack of dogs. That is the main thing that they're good at. But even then, if you show them a cartoon dog, they completely fail. They think it's a safety pin or a disc brake or something. Whilst humans can reason about this sort of thing, like it's an abstract version of a dog. It's not, the pixel statistics are different, sure, but who cares? To other kinds of things, like there's a lot of evidence that sort of neural networks use very simplistic reasoning. So in this case, this is a very nice blog post on Distill, where you can just change the semantics or what the network thinks it is just by putting in some distraction somewhere. So it's clearly to us, it's still a pan, but you just chuck a bit of, pasta to this top left, right, or top corner, and then it thinks it's a wok, because woks are usually used, for cooking noodles. To all kinds of other things. In this case, compositional reasoning. So this is a network. What? Yeah, so this is a network that sort of describes what's happening in the scene. So one of the main things that these networks are lacking is an ability to do causal reasoning. And this is also like, it's one of the fathers of the three sort of horsemen of the AI apocalypse, or if you want to call it, if you're scared of AI. They all agree that, in this case, I'm not saying I want to forget about deep learning. On the contrary, I want to build on it. But we need to be able to extend it to do things like reasoning, learning causality, and exploring the world, and also learn and acquire information. If we really want to approach human-level AI, it's another ballgame. So what about those nice, cool robots that always get shared on Facebook and whatnot? So this is from Boston Dynamics. Look how cool they are. They can do all sorts of very impressive things. Slow-mo. Okay, maybe you don't need the slow-mo. There's also in Boston, this is how Christmas is celebrated. So it actually turns out that they don't use almost any machine learning, unfortunately. So they mostly use classical control theory. So this has led some skeptics. So there's like quite a pool of sort of skeptical types that think that everything is just wrong with deep learning and it has to be thrown out, and that an AI winter is coming. I also obviously had to put some Game of Thrones reference in here. So I disagree with that. Like, we've had incredible progress in AI, but there's, oh no. But we still have a vast amount to learn from the brain. So humans still outperform our current AI systems in many, many ways. They're much more robust. They just, as soon as they have to do many tasks together, or if they have to learn quickly, they're just vastly better. So it's sort of a call to action to say, we still have a lot to learn from neuroscience, from our own brains. So don't just ignore that. Cool, thanks a lot. Went over. We've got 2 minutes under.
A lot. To put you on the spot, how long do you think it'll be before we have AGI?
I was going to ask how long it's going to be before someone asks me this question. Do you want to have
So there's actually a serious question here. Do you want like a map estimate or like a distribution?
Math is fine.
40 years?
40 years it's like nuclear fusion. Like it's always like 20 years in the future. So as soon as someone says 20 years in the future, like it's basically, I don't know, it means they have no idea. So what gives me trouble is that just how, like it depends how much complexity is required for true intelligence. And, like Moore's law is kind of ended. It's not, to get to the point where we have something similarly complex as the human brain is quite difficult. And
So maybe I can rephrase it. What's the minimum time that would really surprise you?
the minimum time that will surprise me.
What's the maximum minimum time that would surprise you?
So I think 5 years, in the next 5 years, it'll definitely surprise me a lot. Like 10 years, there could be some incredible discoveries. Like, I mean, the rate that the rate that AI has been evolving in the last, 7 years or something, if that continues, then maybe it's like another 20 years. I don't know.
Thank you.